Last time we said that a matrix A is diagonalizable if there's a matrix D that's a diagonal matrix and a matrix X that's invertible, where D is equal to X inverse A times X. We talked about some facts involving diagonalizable matrices. The first fact was, if we have a matrix A that's diagonalizable, then the columns of X are eigenvectors of A, and the diagonal elements of D are the corresponding eigenvalues. We said that the matrix A is not unique, and we said that if A has indistinct eigenvalues, then A is diagonalizable. Let's look at a couple of examples where we need to diagonalize a matrix. So here I have a 2 by 2 matrix, 5, 6, -2, -2, and I want to diagonalize it. So what we need to do is we need to figure out the eigenvalues and the eigenspaces corresponding to those eigenvalues. That's the first thing. So let's find the characteristic polynomial. So the characteristic polynomial is equal to the determinant of this matrix, let's call it A, minus lambda times the 2 by 2 identity matrix. So this is the determinant of 5 minus lambda, 6, -2, -2 minus lambda. Okay, let's take the determinant, which is 5 minus lambda times -2 minus lambda minus a 6 times a -2, which is, I'm going to pull out this negative here, make all of these positive. So we get -10, a 5 and a -2 makes a +3 lambda, minus lambda squared plus 12. So we get a lambda squared. If I distribute this negative, a -3 lambda and a +2. Now this polynomial is factorable. It's actually something pretty easy to factor. We need two numbers that multiply to give us 2 and add to give us -3. Those two numbers are -2 and -1. So this factors into lambda minus 2 and lambda minus 1. So we have two eigenvalues. Our eigenvalues are lambda is equal to 2 and lambda is equal to 1. Now let's find the corresponding eigenspaces. So we're going to start with the 2 eigenspace. All right, so to find that, we need to find the null space of A minus 2I. So we're going to take this matrix and subtract 2, 5 minus 2, and then -2 minus 2. So we get 3, 6, -2, and -4. Just want to double check. Okay. All right, we want to put this matrix into reduced row echelon form. I am going to divide the top row by 3. If I do that, I get a 1 and a 2. And notice that if this is a 1 and a 2, this row is just 2 times this one, the -2 times this one. So we can get rid of that bottom row. Now we're going to find the null space, so we make an augmented matrix, and we get that x1 is equal to -2x2. So x2 is free, so let's let it equal s. So we get the span of all vectors. Okay, let me write it like this first. Vectors that look like s -2s, or -2, 1 times s. So this eigenspace is the span of -2, 1. Okay, now let's find the one eigenspace. I'm actually going to just to make sure that I have room below, I'm going to just erase a few things here. Make sure you pause the video and copy everything. And I'm going to save this piece. Okay, so we want to find the one eigenspace. So we're going to take A and subtract 1 times I. All right, so this was a 5, and then we subtract lambda, we get 4. 4, 6, -2, and this was a -2, subtract 1, you get a -3. So notice that if we double this row, we get a -4 and a -6, and it would cancel this row, or you could divide this one by 2 and cancel this one. So we can say we get rid of the bottom row, divide this one by 2, actually divide it by, if we divide it by 2, we get 2, 3, which we then can divide by 2 again and get 1, 3 over 2, 0, 0, 0, 0. And we have x1 is equal to -3 over 2 x2. So then this null space, if we let x2 be free, so let's label it S. So our vectors look something like -3 over 2 S, S. I don't really like fractions all that much. So what I'm going to do, remember that any multiple of this is also a basis. So I'm going to multiply this by 2, and I get that this null space is the span of the vector -3, 2. Right? Because it's the span of this vector, and so just a linear combination of that vector would also be a basis. And I just multiplied it by 2 to get rid of that fraction. All right, so we have our 2 eigenspaces. Don't know why I forgot my P there. So now we can build this matrix X and diagonalize. So we can write a diagonal matrix and the matrix X for this matrix here, A. Let me just get some space here. Okay, so we said for lambda is equal to 2, we have the eigenspace -2, 1. And for lambda is equal to 1, we have the eigenspace -3, 2. And then we have x inverse AX is equal to D. Or if you're like me, I would prefer the notation A is equal to X D X inverse. So it really doesn't matter which way you write it. And on a test, I'll accept either as long as you are able to find the matrix D and the matrix X. The only thing is, notice that I have X inverse here and an X here, okay? Because this is actually the definition they give you in the book for a diagonal, to be able to diagonalize a matrix. Here I have solved for A. I'm going to use this one over here, but you're going to get the same thing no matter what. And this matrix A corresponds to the eigenvectors. All right, so we choose a vector in the eigenspace, this one right here, and remember that these are linearly independent, because well, we've talked about this. We said these are linearly independent. So I'm just going to take these two vectors. So I'm going to say x is equal to, now I'm going to say -2, 1, because this is my first column, and then -3, 2. So this one corresponds to the 2, lambda is equal to 2, and this one corresponds to lambda is equal to 1. So we get that x is equal to the matrix -2, -3, 1, 2. Okay. Now the matrix D, okay, we're going to put, right now I'm going to put lambda 1 and lambda 2, and I'm going to explain how you keep it straight. So this is the first eigenvector, and that's going to go with the first eigenvalue you see. This one is the second eigenvector, so this is going to go in the second diagonal entry here. Okay, so then D, because this goes with lambda's 2, we put a 2, 0, 0, 1. And we say that A is equal to, here I'm putting an x, so -2, -3, 1, 1, that's 1, 2, times D, because this is our matrix X, times D, which is 2, 0, 0, 1. And now we need to find X inverse, which is also a 2 by 2 matrix. Several ways to do this. You can use that little property where you switch these two and multiply these by negative and 1 over the determinant. Or you could just get this in reduced row echelon form. So maybe I'll do that way. I'm going to do that down here. And you put the identity matrix here. And let's put this into reduced row echelon form. So this is, we could switch these two. Okay, so we switch these two rows, then multiply this one by a 2, and add it to the bottom one. So we get one. Okay, and just make sure I didn't do anything wrong. That happens. I think we're good. And then we multiply this one by -2. So we get 0, -2, -2, -4, and add it to the top. And we get -2, -3, 1, 2. So this is our inverse. This is X inverse. Okay, and I'm going to put that right here, -2, -3, 1, 2. So that is X inverse. And notice that it's actually X, which tells us that X squared, because X times X inverse is the identity, that X squared is the identity, because X is equal to X inverse. Anyway, now we have diagonalized the matrix A. And it looks like this. Great. So you could also, if you want to, you can write this as D is equal to X inverse AX, just that X inverse would go here, and then this matrix would go on the back here, and the matrix A would go in the middle. Let's check this. I'm just curious. I want to make sure we got the right answer, and this is a good thing to do on like a test or something. Let's multiply these three matrices and make sure we get A. So A was, just to recall, so this is 5, 6, -2, -2. I'm going to multiply these two matrices together first. This one just doubles the first row, so we get -4, -6, 1, 2. And then we have this -2, -3, 1, 2. Multiply these together. Okay, we get 8, 7, 6, 5. -2 times -4 is 8, and I add a -3. Then we have a 12 minus 6, which is 6, -4 and a 2, -2. Just multiplying these, you see that you actually get 6 and 4. Yep, you get the right thing. Great. Let's do one more. And by the way, this was an example of the last fact. The last fact we had was if A has, so A was an n by n matrix. So if A has n distinct eigenvalues, then A is diagonalizable. Here, A has 2 eigenvalues. This was a 2 by 2 matrix, so we saw that it was diagonalizable. And we were able to just put the eigenvalues here. I want to look at an example where we don't have n eigenvalues. And I want to show you that this particular matrix is diagonalizable and how to handle this. So the next one, I actually moved it over here. I want to diagonalize this matrix. This is a 3 by 3 matrix. So we're going to handle this basically the same way we handled the last one, which was we need to first figure out the characteristic polynomial. So to find the characteristic polynomial, we're going to take the determinant of this matrix. You can call it A minus lambda times I, where I is the 3 by 3 identity matrix. So we want the determinant of 1 minus lambda, 2, -1, 2, 4 minus lambda, -2, then we have a 3, 6, and a -3 minus lambda. All right, we need to take the determinant of this matrix. So this might take a little bit of time. I'm going to go over it and I'm going to tell you what the determinant is, and you just need to double check it. So this is, so what you do, remember, I'm going to go along this first row. So this is 1 minus lambda times, well, you cross this one out and cross this one out and take the determinant of this smaller matrix. This is 4 minus lambda times a -3 minus lambda minus a -12. Okay. Then you subtract 2, cross this one out and this one out. You have a 2 times a -3 minus lambda, and then a plus 6 because you have a -6, so you subtract a negative. Okay. And then we're going to do plus a -1. This is 12 minus 3 times 4 minus lambda. That's just following the formula for the determinant. You need to FOIL all this, like expand this, try to simplify as much as you can, and if you do it right, then you should get that this is equal to negative lambda squared. Well, actually, let me write it completely out. So it's negative lambda cubed plus 2 lambda squared. So anything that didn't have a lambda goes away, including things with just a lambda to the power 1. And that makes sense that we should get a cube because remember, this is a 3 by 3 matrix. It should have a degree 3. And if you factor this, this is negative lambda squared, lambda minus 2. So this is the characteristic polynomial. And from here we can read the eigenvalues. We see that lambda is equal to 0 with algebraic multiplicity of 2, and lambda is equal to 2 with algebraic multiplicity of 1, because that's the power here. I mentioned in the first video that a matrix is diagonalizable if and only if we have that the geometric multiplicity is equal to the algebraic multiplicity. So we're going to see that in this case. Now it could, for a different matrix with these eigenvalues, we could have that the algebraic multiplicity is 2, but the geometric multiplicity is 1, and so that matrix is not going to be diagonalizable. But for this particular example, we're going to see that it is in fact diagonalizable because we're going to get the dimension of the eigenspace equaling 2. Okay, so let's find the corresponding eigenspaces. So let's go back up here so we can see the matrix. Oops, not that far. Okay, here's the matrix. So we said we had 2 eigenvalues. They were 0 and 2. Let's find the 0 eigenspace. So I'm going to subtract 0 from the diagonal, which means I just leave this matrix as it is. So the 0 eigenspace is the null space of A minus 0 times the identity, or just the null space of A. All right, so we need to take the matrix 1, 2, -1, 2, 4, -2, 3, 6, -3, and put it into reduced row echelon form. One thing to notice is that this row and this row is just a multiple of the first row, right? If I multiply this one by 2, I get the second row, and if I multiply it by 3, I get the third row. So the reduced row echelon form looks like this. Make an augmented matrix, and let's find the null space. This is just x1. Remember, this is x1, x2, x3. This is equal to 0. These are the coefficients in front of these variables. So x1 is equal to -2 x2 plus x3. So this is our defining relationship between those variables. And we can see that we have 2 free variables, so we can let x2 be r and x3 be s, and we get x1 is -2 r plus s, and we can find a basis because the vectors that live in this null space look like rs -2 r plus s, which is r times -2 1 0 plus s times 1 0 1. So this null space is just the span of these 2 vectors here. -2 1 0 and 1 0 1. Okay, so let's get rid of all of this. Okay, let's find the null space, and you can see, by the way, that the algebraic multiplicity is equal to the geometric multiplicity, which is 2. Let's find the E2 null eigenspace, which is the null space of A minus 2 times the identity. Okay, so just subtract 2 from the diagonal entries, and we get, so 1 minus 2, 4 minus 2, and -3 minus 2. Okay. So we get -1, 2, -1, 2, 2, -2, 3, 6, -5. Okay, and now we want to put this matrix into reduced row echelon form. I'm going to multiply the first row by a 2. and add it to the second row. And then I can also multiply the first row by a 3 and add it to the last row. From there, notice that if we multiply this row by a -2 and add it to the bottom, it cancels out the bottom row, so we get -1, 2, -1, 0, 6, -4, 0, 0, 0. And I'm going to multiply the first row by a -1, so I'm going to switch the signs here. And then I'm going to divide this row by 3 and then add it to the top row. So I'm going to say that this is a 0, 2, -4/3. I divided this by 3. I got to divide by 3, -4/3. And this 1 is the same thing as 3/3. So now we add this and we get 1, 0, 1/3, -1/3. And then also let's make this pivot equal to 1. So this is 1, -4/6, which is the same thing as -2/3. 0, 0, 0. Okay, now we have this matrix in reduced row echelon form, so we can draw a line here and put 0, 0, 0 to find the null space. We can see that x1 is 1/3 x3 and x2 is 2/3 x3. And from there we have that just want to make sure I didn't make a mistake. Divide by, yeah, I think I'm okay. So I switched the signs here. Okay, and from there I get that if all x3 is, we can give this letter R or something like that, that the E2 eigenspace is equal to the span of 1/3, 2/3, 1. Right? Because the vectors look like R, 1/3, 2/3, 1. And this has geometric multiplicity of 1. Okay, great. Let's copy this and move it up with the other eigenspace. Move it up just a little bit more. Okay, so we know that we have two distinct eigenvalues, 0 and 2, and 0 repeats 2 times because the algebraic multiplicity of 0 is 2. And we can come up with our matrix X and our matrix D. Okay, so I like to write it like this. And all we need to do is we just need to put these basis vectors, -2, 1, 0, 1, 0, 1. Doesn't matter what order you put them in. In fact, you can mix all of these up. I'm going to multiply this vector by 3 because I don't want to deal with these fractions here. So I get 1, 2, 3. So I just multiplied this by 3. And so this corresponds to the 0 value. This one corresponds to the 0 eigenvalue, and this one corresponds to the eigenvalue 2. These vectors are linearly independent. And now we can write our matrix D. Remember, the first column goes with the eigenvalue 0, so that goes in the first diagonal entry. The second column, that goes with eigenvalue 0, so that goes in the second entry on the diagonal. And then the third column goes with lambda is equal to 2, so that goes in the third entry. So now we have the diagonal matrix, and we have the matrix X. And all we need to do now is find the matrix X inverse. By the way, you could, if you want to, you can mix these up. You can say X is, let's say this is -2, 1, 0, 1, 2, 3, 1, 0, 1. So this one goes with lambda is equal to 0. This one goes with lambda is equal to 2. And this column goes with lambda is equal to 0. The only difference is your diagonal matrix is going to be 0, 2, 0, like this. Okay, and of course you can switch those as well. You could put the 1, 0, 1 here and the -2, 1, 0, and you'd get the same thing. Or you could put 1, 2, 3 first and put the 2 here. Anyway, doesn't matter the order, but just be careful that however you order this matrix X, that determines what goes on the diagonal. Okay? So what are we doing next? Well, we need to find X inverse, and then we'll be done with this problem. So X inverse, to find that, we're going to have to, we can put a line here and put the 3 by 3 identity matrix. I think to save time, I'm going to actually just tell you what that is. Well, actually I need to find it because I wrote it differently in my solutions. So here we have -2, 1, 0. If you don't want to watch me go through this, just fast forward the video to where we find the inverse. So this is the matrix X with the identity matrix here. And then we're going to get this into reduced row echelon form. I am going to multiply this row by 2. So I'm going to, let me write it over here first, 1, 0, 2, 0, 1, 3. Keep these the same. And I'm going to multiply this one by 2. So this is 2, and this becomes a 4. This one becomes a 2, and then I'm going to add it to the top one. So we get 0, 1, 5, 1, 2, 0. And then I am going to switch these two. So I get 1, 0, 2, 0, 1, 0, 0, 1, 5, 1, 2, 0, 0, 1, 3, 0, 0, 1. Just make sure I didn't do anything bad here. I think we're okay. Okay. Now I want to get rid of this 1, so I'm going to subtract this row. So I have 1, 0, 2, 0, 1, 0, 0, 1, 5, 1, 2, 0. Subtract everything. And then add it to the last row. Okay, then you can divide this one by a 1, by a 2, and then you'll get a -1, and then you can add it, like multiples of it, to get rid of this stuff. So I'm going, in fact, I can just add this one to row 1. I get 1, 0, 0. This becomes -1, -1, 1, just adding this stuff here. 1, 2, 0. And then divide this by 2. Let's do that. This becomes a -1. This becomes a -1/2. This is a -1, and that's a 1/2. Then multiply it by 5 and add it to the top. Okay. Then we get a -5/2 plus 2/2, that's a -3/2. Multiplying it by 5, so we get a -3. And then 5/2. And then the last step is to make this a +1/2, a +1, and a -1/2. Okay, so I think this is our matrix X inverse, but I may have made a small mistake. I'm sorry about that if I did, but I'm pretty sure I didn't make any mistakes. Just double check it. If you see a mistake, let me know. And all we have to do is say that this matrix X, I'm going to copy it. Let's put it right here. This is X. If we multiply that with this matrix D, put that here. And then we multiply it by this matrix X inverse, which I'm going to copy and paste. Then this should actually equal the original matrix A, which, if we scroll back up, is this matrix right here. So this is X, D, X inverse is equal to A. And a good exercise is actually to compute this. This would zero out these two, so you're only doubling this one right here. And then multiply this with this matrix here and see if you get the same thing. Again, if I made a mistake, it would be right here, finding the inverse. But I feel like it was pretty good, like I did everything okay. But again, you can just double check me and let me know if there's a small error with that. All right, let's move on. So the next thing I want to talk about is things we can do with a matrix, and if it's diagonalizable, how we can calculate things quickly. So we're going to talk about polynomials of matrices. Just like a regular polynomial, like this one right here, you see that we have p of x is equal to x cubed minus 2x plus 1. We can talk about polynomials involving matrices. So instead of this x, we could put p of a. Now, here I'm assuming a is a n by n, a square matrix. This is equal to a cubed minus 2a plus the identity matrix. That's how we're thinking of polynomials involving matrices. Now we're only going to be dealing with square matrices because we want to make sure we can multiply matrices and so on. And so this identity matrix, so if you don't have a variable here, we substitute if it's just a constant. So if this was actually like a, let's say this was a 5, then right here I would put a 5i. So wherever there's an x, I'm putting the matrix A, and if it's just a constant, I put that constant times the identity matrix. So we know that the exponential e to the power x can be written as a polynomial. This is 1 plus 1 over 1 factorial times x plus 1 over 2 factorial x squared, and so on. So you can write this in summation notation. This is I is equal to 0 to infinity of 1 over I factorial x to the I. That's the definition of e to the x. And we can also do this with a matrix. So e to the a is going to be the identity matrix plus 1 over 1 factorial times the matrix A plus 1 over 2 factorial times a squared, and so on. So e to the a, you can think of it as the sum, where I is equal to 0 to infinity, of 1 over I factorial, the identity matrix, times a to the power I.